Alright, so for example, here we have the mapping of the square root function, square root of z squared minus 4. And as you can see here, we have the right hand side is the function plane, or the target function plane, and the color just represents the angle. And you see here that the upper half is defined by this branch cut and automatically defined by the dashed line, because the function square root maps the z-plane into a half plane in the f of z plane. Okay, so the interesting thing here is, well, we can see the mapping of the z-plane in the of the f of z-plane in the z-plane, and you can see here there's a discontinuity, right? So there's two discontinuities on the color, basically represent the branch cuts, and they're just the effect of the branch. So because this point here is mapped over here, and if you go around the circle, this point here is mapped over here, and it kind of makes sense. So for example, in this case, this point here would be the square root of some number times e to the I2 pi, and when you take the square root, the exponential I2 pi divided by 2, because exponent of the square root is 1/2. This means that now you have e to the I pi, which is well, -1, or about here in the red region. Okay, so the cool part about this interactive app is that you can place a branch cut anywhere. So if I drag this little circle here, I can move around the position of the branch cut, and you can see what happens in the z-plane automatically, which is very cool. And this actually shows that how things are, and basically where the branch cut is going to end up. So for example, let's say that we're mapping the right hand side of the plane. So you can see here that the branch cut looks like an L shape here and here, but as I move it ever so slightly, you see that it's actually like a hyperbolic curve that eventually kind of collapses onto itself, and then it crosses out to the negative of the hyperbolic curve. So, which is a very interesting behavior. And as you can see here, the only difference, you see the function is the same. It's just that now we're looking at the z-plane, or we cut in the z-plane such that it maps to the f of z-plane in this way. And we can place the cut anywhere. And for example, if we place the cut at about 45 degrees, which would be about here, then we get this hyperbola on each one of the branch cuts. And if we change the position of the branch to the other side, we get a hyperbola to like facing the opposite direction. So this also clarifies something that for me was very confusing, which is sometimes you're talking about the positive branch or the negative branch of the function. So for example, here I'm highlighting, or like I'm showing in vivid colors, the upper half of f of z, which basically would mean that I'm looking at the roots of this argument such that the root is argument is between 0 and pi. If I move this to the lower half plane, the only difference, the function is the same. It's just that I'm looking at the second branch of the function. This is basically what they mean by the function branches. It's like I have two answers. So in the case, for example, if you're looking at the right hand side versus the right hand side, you're looking at the positive root of the square root of the argument. If you're looking at the left hand side, which would be this side, then you're looking at the negative root, because as you probably already know, the square root function has two roots, so the positive and the negative root. So this is what they mean by positive negative root, but you can also do it in any angle possible, and this gives you this very interesting patterns to look at.